photosensitive detection. I know you have digital cameras. They are equipped with such things. The surface is divided here in small pixel arrays, and each array is sensitive to light, to specific light. It has three, pixels, 3 points. Each one is specific to a color. So this is how the image is built. You have a large number of pixels, sure, you get a very good resolution. And these resolutions at this time, non-standard resolution, talk about 40,000 megapixel or so. We still have to go 3 times more to get to the resolution of the human eye. Magnetic field sensors in any hard drive, on laptop or whatever hard drive is not large, is small. We have these magnetic heads. They're usually magnetostrictive. What happens when magnetic media passes around the sensor, close to the sensor? The sensor will modify either resistance or will modify some impedance. So this is used in this type of application, but could be used for proximity sensors. Unfortunately, this type of sensors are limited by the Curie point. If we use soft iron and alloys, the Curie point is in about 700 degrees range. But we cannot go more than half of that because the capability of magnetic, ferromagnetic properties decay. Our other inertia-based sensors, we talk about accelerometers that could be 3 axes, 3 dimensions in one single chip. We talk about gyroscopes. Gyroscopes have evolved terrible for last 5-10 years. I recall the first time I saw one was bulky, about the size of this thing, and extremely expensive. Now you could buy for about $12 a gyroscope on the shelf again. If you want to buy OEMs, the cost will be definitely much less, right? So one could get from here the velocity from gyroscope, the rate, the rotation, right? And eventually, so now for optical, one could get optical detection in any ways. Could get displacement, velocity, acceleration, vibration, even spectrum. You say what is spectrum, we'll get the consistency of specific gases, what the gas is made from. But this is a principle shown in here is the vibration detection. I could have a small mass vibrating. Why small? Because I could catch very high frequencies. As the mass is small, resonant frequency will be high. I have a linear domain of detection up to 0.8 of the resonant frequency. And then optical, because I have very fast response time. That would be the... This is another type of sensor, but it's a saturation, oxygen saturation sensor, but it's based on the same thing, on oscillation of 2 different light of different wavelengths, blue and red. And this gives basically what is the content of oxygen in blood through the skin. Magneto-optical detection, basically this gets into detecting the magnetic pattern of an optical medium. The first application of that was in some imaging in the human body. It's a laparoscopic ultrasound transducer for augmentation of what is seen inside the body. But the same thing could be used, for an example, into the engine to instead of the boroscope to check, certain capabilities after service of the engine or before service or whatever. So current sensors, the sensors market definitely continues changes. What we have here is 2008, I think. That is the last time when we perfected this review. You probably will find out, other capabilities, better capabilities of certain sensors. The performance of sensors is general ranging with the same limits, not because the capability of companies are same, just because of the requirements. I have automotive as a pool technology. They will ask for specific requirements, and there will be multiple companies doing the same type of capabilities because this is what is required. This is what they are going to deliver. Not because, oh, this is my limit. Limit could be definitely expanded. And I have here put a sentence, I think, from myself. There are sometimes new principle of new materials that will have the faster advancement in measurement technologies. And there are a few examples of that. Silicon carbide. You might say, oh, this is something we knew about. Yeah, but we didn't know since 10 years ago, 12 years ago, that we could have full electronics on the silicon carbide. Did not progress. It's very true because there was no pull. Everything is a push from a group of people. We have components, have diodes, we have transistors, unique transistors on silicon carbide, but we don't have an integrated circuit. Although the efforts 10 years ago in Case Western Reserve University, they would offer multi-user technology for integrated circuit on silicon carbide. I mean, you could send a design, they will send you back the chip and say, this is your chip, to pay a fee definitely for the service. And you can test your design on silicon carbide. But again, because there was no interest, or the interest was no pull, the technology was basically postponed. Exactly what Sanjay mentioned, we have a TRL6, but it came late. And, you know, the design already has commenced, and we have to wait. It's a dead technology for some time. So now, what is present available on the market? What we have as temperature sensors, thermocouples, and you see range here. Ranges are, you know, I should say from minus 250 to 1,700, and according to the dislike materials that are joined there. They also, they bear a type. You can ask for a type specific thermocouple. For example, B, we know that goes to 1,700 degrees, right? Rhodium platinum. They are packaged, they look like that, these sensors. You could also acquire them as simple wires and eventually welded or not, according to your requirements, your needs. They are slow. They respond slow because of the, you know, the thermal process. That is not a fast process, but they are good enough for the application they are using. This is a temperature. We discussed about those. They are much more accurate because they could basically measure variation of temperature of 0.2 degrees or of 3 degrees, and their drift is about 0.1 degrees per year. What does it mean? I subject the sensor to a temperature, I cool down. Subject, cool down. I could tell you from my experience, these B-type sensors, I have an oven that I heat it up at 1,700 degrees, go down. It lasts about 10 cycles, and I have to change it. I know already. I don't wait, you know, to lose whatever I have in the oven. So I know every 10 cycles I change the thermocouple.
So a sensor like that, I mean, you have to attach it to some power device. So you have to have a power.
This one, yeah, you need a power.
You need a power, and then output is an electrical signal. It's like
this is a variation of resistance, right?
Yeah. So and then you have to convert an electrical signal into the temperature based on a charge provided.
Right. Exactly. Yeah.
So, okay, I wanted to understand that. So
yeah.
We as sensor guys, we as controls guys say sensor is the whole thing, you know.
Right.
Yeah. I just units, but
the issue is indeed
you just measure the current.
Yeah.
If you apply a certain voltage,
you
see the
current,
current,
you take the
go
current
to
and
your calibration table.
calibration table. Okay.
but this calibration table is usually
It's a linear law.
linear law. It's very linear, and it's somehow built with a constant in the sensor. So what you get right away on indication. You have a indication unit, get the temperature. You don't get the current, right? Because it multiplies by the constant of the sensor.
Yeah.
But they are packaged, as you say, for the specific requirements, the harness and the application. They are, you know, bulky. They are big. Although the sensor is just a small wire of 1 millimeter of platinum. It's not a big thing. It's a small, but because of the certification, qualification.
This will be measuring air temperature, so you would put that little wire in
Right.
the stream of air.
Yeah.
Okay.
This tip goes in
It
the
goes in the stream.
air, right? Exactly. But you have to go through the access hole, and you have to assemble this. You have to make sure that you have a connector here, and all this 0.01 gram will become half a pound or so.
Is it hot wire measurement or nothing to do with
It's
it?
not hot wire.
Oh.
No, it's not. It's not that hot wire.
Just to add one thing, the problem with thermocouple or thermoresistor measurements really is the time constants
Right.
of the device. And typically there are two time constants. One is the heat transfer from the flow to your device, and the other one is just the thermal inertia of the device. And we have thermocouples in helicopter engines, and we cannot measure the true gas temperature peaks,
Right.
but we are always lagging behind by something like 1 second or so.
Okay.
And so we might have true gas temperatures that are 200 or 300 or 400 degrees higher, but we simply don't see them on the sensor because it takes some time
Get there.
just from the thermal inertia and from the heat transfer to
The resistance temperature devices, they perform a bit better than the thermocouples. This is one point. But again, they need power supply. I mean, it's a different
So
total
these
approach.
won't be good for dynamic measurement. These will be good for steady state.
It's for steady state.
Well, they are used in the control system. You don't use, typically you have in engines, you have the ring of thermocouples, say 8 or 10,
And the test
wired
ring.
together, and in production
Even
engines.
production.
Production engines. It's the typical temperature measurement device is a ring of thermocouples where you do some averaging and plausibility controls, but that's the for instance, exhaust gas temperature.
Oh, exhaust gas.
It's
It's for
exactly
the exhaust
measured.
gas temperature.
Yes, but
Right.
that's
Only
the only,
measure.
typically the only
Yeah.
measurement you have.
Right.
And then you build in that delay in there. Basically, you know there's a frequency delay. So it's
Well, you could try to compensate for the delay, but that's based on
Unknown.
speculation.
And also it's steady state measurement, at least in land-based gas turbines.
Right. I mean, you also don't expect probably very fast changes in the exhaust temperature unless something happens that engine shuts
However,
down.
if you accelerate the engine fast, you have the temperature spike, but you don't see it. The material sees it.
materials.
I'm just curious, what are the dots on that sensor on the right? Is that just dirt?
No, I think it's just that I took the picture from the internet. It's no,
Okay.
I don't think it's anything. Maybe dirt or
Melting.
The filament
Mercury.
belt.
Right.
To show what.
Okay, so we have here. This is probably it's a good point in here. Let's look at the linearity, moderate temperature range, stability. We talk about stability degrees per year. So thermocouples they have a higher drift, that range. Accuracy, the same thing as we talk about. You see, linearity, moderate and good. It's very vague, qualified, and nobody will give you the response time. They will say good, or because that is according to the application, how fast you change the temperature. If you have a change of 3 degrees, probably you'll never feel it. Have a change of 50 degrees, probably will feel it in 3 seconds or